Okay, you remember from last lecture, a simple closed curve is one that can be obtained from a circle by continuous one-to-one deformation. And we took some examples of that. Okay, it's basically just a messed up circle here. Okay, we mentioned this in context of a theorem involving curl. Okay, I claim the following. If this particular vector field is conservative, okay, presumably in some open region of the xy plane or region of space, then when its curl should be 0. Okay, let's go ahead and I'm thinking 3 dimensions here. Say f is m, n, and p, so functions of x, y, and z, right? Each of these. Okay, and then what? There exists some potential function, which I'm calling here little f, that actually gives rise to this field. So that means little f sub x should be equal to the what? The m. Little f sub y should be the n, and little f sub z should be equal to our p, right? Throughout this open region. Okay, alrighty. Then what would the curl be? Okay, notice we're using our compact notation here. If you want to, you can include the ijk here. Okay, but anyway, let's compute the curl of f. Okay, now this is acting like operator, right? Remember, this is what? This is operating on f this way, right? Remember how it goes? Okay, that's how to compute the curl. Okay, so we've got ijk up here. The second line is the partials, and then the last line is the m, n, and p, which correspond to the f sub x, f sub y, f sub z, right? Okay. Let's get rid of this. Now, let's actually compute such a thing. Okay. All right. So we would first do what? We would do this right here. The partial derivative of, so f sub z with respect to y, that would be what? Remember the order with the subscript? That would be f sub z y. And you'd subtract from that what? F sub y z when I take the partial derivative there. Okay? All right? And you go through each of the components and you go through and do the same thing. And take a look what we end up getting here. I've got what? F sub yz minus f sub zy minus f sub yz, f sub xz minus f sub zx, f sub yx minus f sub xy. What are those going to be equal if all these second partials are continuous? Remember, we had the mixed partials theorem. If those are continuous, then these are all going to be what? 0, because it doesn't matter what order we take our derivatives in, right? Our second partials in. Okay, so there we prove this statement, at least under what? The continuity of the second partials there. Okay, all right. This doesn't give complete proof by any means of the theorem we were talking about in the last video, but that's okay. We're not going to go through that complete proof anyway. Just remember when we're testing for whether we've got a conservative field or not, a potential field, right? We're going to check the curl and see if it's 0 over a simply connected region that we're dealing with here. Okay, let's talk about another theorem here called the fundamental theorem of line integrals. Okay, this is an important theorem here. I guess I've only written it in 2 dimensions here, but you can certainly do this in 3 dimensions. Okay, maybe for ease here I just wrote it 2 dimensions. I've got my vector field given by what? M and n, right? Okay, so there's my f bar. And then let be a vector field in which the component functions m and n are continuous in some open region R of what? This would be in the xy plane then. Containing this piecewise smooth curve C. Okay, so that's in there. And here's the endpoints. Okay, The endpoints of this curve are x1, y1, and x2, y2. So those are coordinates of the points there. Okay? Alrighty? And presumably we're going to be integrating, when we're talking about integrating along C here, we'll be going from x sub 1, y sub 1, to x sub 2, y sub 2. Okay? Alrighty? Now, if I'm dealing with a potential field, notice here, I'm assuming the existence of what? A potential function whose gradient gives rise to f, okay, throughout the region. Then what we can do is the following, okay? The line integral here, f dotted dr, integrated over c, is going to be this then, right? Okay? And it's going to be this, okay? It's actually equal to this. To actually compute the value of this, what you do is take the potential function and evaluate it at the two endpoints and take the difference. See, it's the function evaluated at this, maybe I should have given a name like A and B here, A and B. Okay, the curve is a curly thing, C. The function evaluated at B minus the function evaluated at A. Now that's the scalar function, right? The potential function. Okay? Alrighty. Now we're going to mention more about that. Yeah, that's kind of an interesting thing. But basically this, let me explain the existence of the potential for the field actually says that you can find in this essence an antiderivative of this thing. Okay, an antiderivative. And you remember the fundamental theorem of integral calculus. What do? You find an antiderivative and you evaluate it at the different endpoints of the integral and take the difference, or the limits of the integral, as some people might say. Okay? The proof of this is not all that hard. We'll wait on that. Let's demonstrate this first. Okay? Okay, let's look at this. I've got f bar is, let's see, 2xy cubed I plus 3y squared x squared j. Okay, so that's my vector field. What would be the domain of this thing, the natural domain of this thing? Do you see it makes sense everywhere? Okay, yeah, I mean, these are just simple polynomials here for your m and n, so this actually makes sense everywhere. Okay, so the whole plane, is the whole plane simply connected? Remember the definition for that? In 2 dimensions, that simply means there's no holes in there. Okay, yep, it's simply connected. Is it conservative? What are we going to do here? Let's go ahead and compute the curl. Okay, so let's compute the curl. So I put the components down here, and we will get what? The partial derivative x, partial derivative y, partial derivative with respect to z here. And then I've got the component functions here. See how we can effectively ignore what's happening over here in that sense, but we're not going to do that. Here, let's go ahead and do this. Okay, you see that these two components are going to end up being 0 because I'm going to have what? I'm going to have my 0 right here, and I'm going to be what? Differentiating with respect to z. So in the case of what? A function of 2 variables, so in the xy plane, we can actually, write a shorter condition here. We'll talk about that. But anyways, let's keep going. So basically, what am I doing? I'm taking the partial derivative of n with respect to x and subtracting from it what? The partial derivative of m with respect to y, like we have right here. So do you see, if we were calling this mi, and this nj, then what we really have here is what? N sub x minus m sub y. Okay? We know these two are going to be 0 anyways. We already mentioned that. Let's look at this. Is that actually equal to 0 here? N sub x minus m sub y? The answer is yes. So we actually get the 0 vector out of that thing. And here's what I'm saying here. In the case of where you're dealing with 2 dimensions, instead of looking at the curl, you could just see if n sub x is equal to m sub y. Anybody that's had some elementary differential equations and has been looking at exact equations will recognize this little condition for exactness. Okay, well, anyways, the point is that this is what? And these are all nice and continuous. F is conservative. What does that mean? That means there should exist, what, a potential function here. Okay, we'll talk about conservative as independence of the path here in a little bit too. But find a potential function for this thing, right? One ought to exist. So in other words, there should be some little f, right? Function of x and y, a scalar function, whose gradient actually gives rise to this thing. Okay? Now, can you actually find such a thing? Okay, could you do it? Okay? Well, there's slightly different approaches people take. Let's see which approach I took this time. But let's start like this. What's f sub x? F sub x is the 2xy cubed. So I'm going to go ahead and integrate that with respect to x, and I would get what? X squared y cubed plus an arbitrary function of y, which I'm going to call g of y. Any function of y, when it differentiated with respect to x, right, partial derivative, then I get 0, right? Okay? Now, f sub y would be what? Well, if I differentiate this thing with respect to y, I would get what? 3x squared y squared plus g prime of y. But what is f sub xy supposed to be? It's supposed to be this thing right there, you see? So it's supposed to just be that. What does that imply about g prime? G prime of y should be 0. That means it's what? It's constant. So what we could have here is that our function f of xy equals x squared y cubed plus an arbitrary constant. Okay? So any potential function of that kind, when you take its gradient, will give rise to this particular field that we started with right here, right? It'll give rise to this thing. Okay? That's good. We're going to use our theorem then. Okay? Now we're going to integrate. Okay? Now this is going to be independent of the path. Do you see when you come back and look at this theorem here that we looked at? Oh, wait, right here. When we looked at this and we talked about this, we found that what? This integral here, when you were integrating across C, only depended upon the endpoints, right? It only depended upon the endpoints here. Okay? Now ready? Any curve C with these endpoints, if I integrated across some other curve C, C2, if this was C1 and this is C2, I would still end up with what? Exactly the same value, right? If I'm still integrating over that potential field, or that conservative field, if you like that term better. Okay? All right, so all we have to do here to actually calculate this then by this theorem, okay, we just found the potential function. By the way, I'm ignoring the c because it's going to drop out, right? And I'm evaluating at the endpoints of whatever curve. You know, I didn't even say what the curve was, okay? And then just take the difference of the two. And I got 31 out of this value. But the value is independent of the path taken from 1, 1 to 2, 2. Okay, that's interesting. Okay, so if you're integrating over a potential field and you've got these 2 points A and B and you're integrating C, the gradient, right? Okay, so this is, if you want, you could call that your cap F for, you know, that's a potential field, right? It's supposed to be a conservative or a potential field, same thing. If you're integrating across C1, you know, across this path C, you're going to get the same value as if you integrate over here. Across this C, same thing as you integrate across here. Doesn't matter. Okay? And I think I illustrate this. The value in this last example here is independent of the path. For the conservative f, All curves starting and ending at the same point B. There, I've got that drawing for you. Let's try this D again here. Here's what I was talking about here. Okay, let's work this problem a little differently along a particular line here. I'm going from what? 1, 1 to 2, 2. How about going straight there from 1, 1 to 2, 2? Okay, that'll be my C. Okay, that'll be my curve here. I don't like that. Okay. Okay, that's my curve C. Okay, so I'm here at 1, 1, and then going to 2, 2. Okay, if it's independent of the path that I am integrating across, right, around, from this point to this point, then why not do the simplest curve of all? What would be the simplest curve you could think of? How about the one that doesn't have any curve to it? How about the what? How about a straight line? Okay. Find the equation of the straight line between those 2 points. Here I take the parametric form. It turns out t is going from 0 to 1. X equals 1 plus t, y equals 1 plus t, right? Okay? Alrighty. Now let's come back here and look. So I'm doing this over this line here. Okay? I'm being very specific about the particular curve this time, right? Alright? And now what's dx and dy? It's the same as dt. And here's my original integral, right? Okay? So that's f dotted with dr. Okay. Get that off there. Okay. Now what do you do in a case like this if you have the parameterized curve? Well, where's t going from and to? It's going from 0 to 1. X is 1 plus t and y is 1 plus t. And dx and dy are dt. So you put those all together in there. Do you see what I'm doing there? You know, working a line integral the regular way, where I parameterize the curve. Okay? And I work that out and I put those together, and this is what I got. I've got 5 times 1 plus t to the 4th power is what that ends up, this expression here ends up being along this particular curve, that straight line. And then integrate it. What would I get? 1 plus t to the 5th going from 0 to 1. That's 2 to the 5th minus 1 to the 5th is still 31. Okay? Still 31. Interesting, right? Okay? Integrate it if you want to. You know, take some other path and just try it, you know, just for a practice here. Take some other parameterized curve, a parabola or something, going from here to here. Oops, I should really be putting arrows on these, right? Traversing in a particular direction. If I traversed in the opposite direction, of course, I'd have a negative sign for my final answer. Anyway, you'll still get what? What will you get in the end? You'll still get 31. Okay? Might seem kind of miraculous, but there it is. Okay? All right. What would happen if I'm integrating? Okay, I've got a conservative field. That means it's a gradient field, right? Okay? Okay, so f, just to re-emphasize over and over again, it's a gradient of some function. Now this can be multiple dimensions, not just 2. It could be 3. Okay, I just did it with 2 dimensions for ease last time. Suppose I'm integrating around a simple closed curve. What would I get if I went like this? What would I get? Well, I would get 0 every time. Does that make sense? Here's how I'm thinking about it. Okay? I've got my simple closed curve. And let's say I've taken a point A on the simple closed curve and B on the simple closed curve. Okay? And I broke it up. Okay, so this whole curve, I'm going to break it up into maybe part C1 and then part C2. Okay? Now here in C1, when I integrate over C1, I can really do what? Because it's a conservative field, I can just be really integrating from A to B. Okay, like I see here. Okay? What would you do? Well, if little f is the potential function, I'd do what to compute this? I'd evaluate at B and subtract what? The value at the initial point A. Okay? That'd be the integral over C1. Now what if I'm integrating over C2 instead? Okay? I'd be going from what? From B to A, of this same form, right? But since, once again, because this is a potential field or a conservative field, then what? I just got to evaluate that potential function at the endpoints and take the difference. But notice I'm taking the difference in the opposite order. And then what happens? We get total cancellation. So the point is, in a conservative field, if you're integrating around a loop, a simple closed curve is sometimes called a loop, by the way, what are you going to get for your answer? You're going to get 0 for your answer. Okay? So that's pretty cool. All right? This has to do, by the way, when the term conservation has to deal with what? Conservation of energy. Okay? For example, when a planet goes all the way around in its orbit, its total energy will be unchanged, right? By the way, here, just the shortcut, I mentioned this a little earlier here, where I was talking about a shortcut for saying the curl is equal to 0 in 2 dimensions. You see, if you were to do this in general here, okay, in just 2 dimensions, this is what we would get for our curl. Setting that to 0, that would happen if and only if what? M sub y is equal to n sub x. I guess I wrote it this way in the previous one. Obviously it means the same thing, but there it is, okay? So I make this statement right there, okay? We're going to use this for a test. But the easiest way to remember it is, of course, that the curl is 0. Just remember you're only going to get a k component in the end. Do it either way you want here. Okay? All right, just throw that in there. Okay, that should be okay for now. We'll work some more of these problems in the next video.